Good morning. Thanks.
Morning, Doug.
For some early calculus. Cody, Alyssa, Eve, and Raymond, and Thomas, and Adrian, and Tom are in the house. All right. Turn the radio off. Let's do this. We are in the thick of an amazing discovery. So let us continue. So if I remember right, which is no guarantee, we figured out a growing expansion for sine of x, which was unbelievably cool last time. And now we must look further into this glory. Let's see, I'm in the mood to write on graph paper today. The engineer in me comes out. So, let's recap just for a second. See what progress we can make. So we're continuing at least for today, maybe even a little bit more into, and I didn't show you this yesterday, I mentioned it, but we didn't get around to it, but we will today, into a Taylor series. Remember, this is just a kind of a cool name for a power series. And we said that all you have to do to find a Taylor or a Maclaurin series was to do this. We said let's actually just do it. I'll kind of write it up here a little bit later, but let's find one for this. Let's find a power series. This is unbelievable. So this curious little number E, 2.718, remember, just because it's kind of cool, that if you take the expression 1 plus 1 over n and raise it to the n power, as n approaches infinity, that's where E actually comes from. And conceptually, that's kind of awesome, because what you're really doing when you divide by n, it's growth, because this one right here represents 100%, and then this is a little bit more added on to that. So in other words, if I was growing at 2%, that'd actually be 102%, because the 2% is the growth and the 100 is what you already had. And so this is growth. And then if you let n be 100, then that means you're sort of dividing your interest rate by 100, but then you have 100 time periods. And so oddly, this number E comes up, well, quite naturally. Natural logarithm comes up quite naturally in the world. And so anyway, that's just kind of a cool reminder. You can ask me more about that after class if that's not familiar to you, because it's kind of neat. And so let's see if we can come up with a power series expansion. Ultimately, we're going to do centered. This language will make more sense after today. We're going to center it at x equals 0. So you remember that E ends up looking something like this. And so we can get it to look like that. And we saw this happen with sine. We can kind of start any place we want. Well, we're going to start with our curve kind of being right here, centered at 0. And so we'll do this in the next question. You could go a little ways away from that either direction, and that'd be fine too. Like we could go out to 2, and we could say, well, and our goal might be to figure out what E to the 1.9 is. And so we could go out to 2, and we could say, let's kind of find a curve that looks like it out there somewhere. We could do that as well. So a Maclaurin series is when you say you're going to get this thing to look like the graph at 0. I think I'm spelling that right. Maclaurin series. So what we said last time is this is how you find the coefficients. You find the derivative And E is, of all things, even easier than sine was on Thursday, because the derivative of sine was cosine and the derivative of cosine was negative sine. Like, that's not a bad derivative to take, but there's nobody who exceeds E in derivatives. And it's really crazy because E is the one equation whose derivative is itself. In other words, if you plug in 1 and you get E to the 1, which is E, not only is the y coordinate E, the slope at that point is E. I mean, it's kind of weird. Like the y coordinate and the slope are the same exact point. And so all of our derivatives, all of them are just f of x. And so this is just kind of a crazy, remember we kind of switched to that terminology when you get out to 4 derivatives, but you got to put the parenthesis there. It looks like f to the 4th. And so we can go as far with this as we want. And all of those derivatives are just e to the x. And therefore at 0, e to the 0 is 1. And so since e to the 0 is equal to 1, does it make sense that that's all of our coefficients? So we said our terms then for this cool, we'll call it a Maclaurin series as a function of x. We know that it's x to the 0 and then x to the 1 and x to the 2 and x to the 3. Again, just a good old power series. It's just a polynomial. We just call it power because, well, those are powers. And so let's see, I took it out to the 5th. So let's go out to the 5th. Let's see. Should I have 5? Should I have an x to the 5th? Like, that's 5 terms. Well, I don't know. Let's see. So basically, this is every coefficient. So I've got to take the derivative and evaluate it at the point that we're interested in, which is at 0. And that's how we got our coefficients. And so in this case, every single coefficient is just 1. And so there's our equation. It's just, I'm done. I guess I don't need to put anything in front of those. Is that true? It's not quite true. What else was a part of the coefficient? I know it's early.
You had to divide by a factorial.
Exactly. So it is 1, but it's divided by, well, 0, in this case, 0 factorial, because we're on the 0th term. And then it's, again, coefficient 1 divided by 1 factorial, and then coefficient 1 divided by 2 factorial. That's exactly right. Coefficient 1 divided by 3 factorial, coefficient 1 divided by 4 factorial. Notice this is a very easy pattern to recognize. On my review and on the test, I'll call this, as your textbook does, I'll call this P5, like polynomial degree 5. So that's a 5-degree estimation. So technically this goes on forever. And if it does go on forever, then that's actually equal to E. And so if I were to, I don't know, maybe write that out a little bit clearly. Again, it's really weird that 0 factorial is equal to 1 and x to the 0 is 1. So that entire first term just turns into 1. And then 1 factorial is 1. So you have 1 over 1. 2 factorial is 2. 3 factorial is 6. And I hope you have a good feel for where that came from, because you're repeatedly taking the derivative. So if you take the derivative of x cubed, it turns into 3x squared. And then you take the derivative of x squared and it turns into 3 times 2 times x. And so that's where factorial came from. And then 4 factorial is 1 over 24. And 5 factorial is 1 over is 120. Let's see that I blew something there. And so that is equal to E. This is amazing. So rather than rewrite it, I think I'll just point out that this is actually equal to E to the X. Wow. So we found a way to expand e. Now you might say that's not inordinately useful, because if I want to know what e to the second power is, I mean, I know that e is 2.718, and as long as I have a regular calculator that even has exponents, you don't even have to have your cool calculator, just a cheesy calculator. You can type 2.718 raised to the second power and get the answer. So I'd say that's sort of not as useful. But here's something kind of interesting. You do this. What happens if you take the derivative of that side over there? Notice again, that's one of the beauties of these Maclaurin series or Taylor series is polynomials are the easiest equation to take the integral, or the integral and the derivative of. And so that's kind of cool. I mean, I'd rather work with those than all the other complicated functions like logarithm and sine and cosine. But what happens if you take the derivative over there?
Everything shifts over left.
Yeah, n prime of x. Well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared, the 2 comes down front. The derivative of 3 times 1/6 is 3 times 1/6. Do you see it working? Isn't this amazing? 4 over 24 x to the third, 5 over 120 x to the fourth, and so on and so forth. Do you see that it actually becomes itself again, just like it should, because isn't the derivative of e to the x, e to the x? Isn't that kind of cool? So just so that it's clear, bam, that turns into 1, bam, that turns into a half, that turns into a sixth. And this turns into 1/24th. And so it's exactly the same series. If it goes on forever, nothing is lost. It went on forever. It's the same exact series. So in a sense, that's a proof that the derivative of e to the x is e to the x. You probably have just been taking that for granted for a long time. If somebody asked you, why is the derivative of e to the x e to the x? Your answer would probably be, I don't know. I guess I forgot. The teacher told me it was, and I believed him. Her. Well, now here's a proof, a way to see that it's true. In my class, I don't know as I ever kind of proved that, but we did notice that even in the calculator, if you take the derivative of e to the x in the graphing calculator, it gives you the same exact answer as the y coordinate. So that's kind of cool. That's kind of amazing. Why don't you try this with so if I remember right, we did sine, and I know either sine or cosine is in your homework assignment anyway, but I think we did sine in class. And so actually, let me show you one thing right now before we do that, before we do one more example. This is kind of cool. So what's a Taylor series? Taylor series. Basically, the only difference between Taylor and Maclaurin in names is just the center. The center is not 0. Now I want you to think about this. What if we wanted to know, what if we wanted to do this e to the x thing, like we're trying to find a model for it, except we didn't want, and I'm going to switch over to Desmos for a minute so you can look at this. So, and also just to give you time to grow in your intuition. So, you know, we just found an expansion for it. And again, you're just sitting there saying, well, I guess that's true. What's wrong with the old internet? Why is it waking up here? Desmos. Go away. So f of x equals e raised to the x. So there's the graph of that. And we are saying with our new function here that I guess I would continue to call m of x, that was equal to 1 plus 1 times x plus 1/2 times, well, I'll get little equal signs in there. I gotta relax. Slow down. I'm drinking a little too much coffee, a little too fired up. Do you notice it is growing as we've seen these things do to look more like E every single time I add terms to it? So there's a parabola. That's what I'm calling in your book is calling P2. That's a polynomial of degree 2. That's the best match you can get. But again, notice it's only a good match. Well, right around 0. That's what this concept of being centered at 0. I don't know if centered is the right word, more like a good match. It's a good match as long as you're right around 0. And so again, it's like, yeah, look at that, really close, but don't get too far away. And if I go on and add yet more terms, 1 divided by 6 raised x raised to the 3rd. Once again, getting a little too excited. I'll get a z in there, man. What's the matter with you? Notice, you know what cubed equations look like. Doesn't it look like a cubed equation? And so it followed it a little bit longer. But what if I wanted, and this is important, what if you wanted to not be close to 0, but what if you wanted it to be close, say out here at 1? Like I wanted it to be centered at 1. You should know this from Math 111. How do you take this same graph right here and get it to, well, move to 1?
Don't you just minus the equation by 1?
Yeah, each individual x, not the entire equation minus 1. That would move it down 1, but every single x. Instead of x, it's now x minus 1. Parenthesis minus 1, close the parenthesis. Man, what is wrong with me today? Failure at the keyboard today. Doesn't that move it minus 1? Moved it right 1. But
Now you got to go up.
yeah, but notice it doesn't kind of match up. It doesn't match up quite right. Like now it's got to go up. How far does it have to go up? And why doesn't it match? Why doesn't it? So first of all, you should see it did slide right 1, right? Because wasn't it right there and now it's right here? So
Would you just add 1 to the entire equation?
yeah, do I add something to it? So I say 1 plus, that would move it up 1. Notice that moved it up 1. But that's not behaving quite right. That's the key here, is like, how are we going to get this thing to kind of be centered? Well, the difference is this, and let's go kind of do it right now. I wish it was as simple as that, because when you move something to the right, it just slides to the right. And so what else has to happen? Well, the thing that we got to write down, and let's go look at this right now. This is what a Taylor series says. It says that if you want to find your series, you do the same thing we did before. You take the function itself, but rather than putting in 0, we'll say this point A. In other words, some other number like 2. We're using 1 right now. So I would say, well, then you have to evaluate the series at that A value.
You're still sharing Desmos right now.
Oh, thank you. We'll go back to that in just a minute. So the key to this is you actually just plugging in a different number. Do you agree that a second ago we were putting in 0 every time? It was e to the 0, e to the 0, e to the 0. Well, now we're going to be putting in the e to the 1. Does that make sense? We're going to have kind of a different answer. We got to plug 1 in now. So we don't have the same exact slopes anymore. Before, our slopes were always 1. Well, what's going to happen now? So this is what a Taylor series looks like. So it's centered not at 0, but at something else. And so our first term was our constant, and then it goes from there. And we said, okay, well, what's our next term? It's f prime of a. That was our top number. And then f double prime. I'm not triple prime. Come on, man. Double prime of a. And then f triple prime of a. And then we divided by 0 factorial and 1 factorial and 2 factorial. Notice that's the first one that actually shows up as something. So I'll go ahead and write these other ones in here. 1 factorial is 1 and 0 factorial is 1. And so you can kind of leave those off since they're ones anyway. And then instead of, and this is the part that's interesting, instead of just x now, well, it's x minus 1 for us. And then x minus 1 squared, and then x minus 1 cubed, and so on and so forth. So that's how you get it not to be centered at 0. So let's see if we can kind of redo E and sort of fix it so that it matches E when x is 1. So that's the difference between a Taylor and Maclaurin. Maclaurin is centered at 0. Taylor is like centered anywhere you want. For that reason, you kind of don't hear the word Maclaurin very much because this formula is kind of the ultimate one. So like sometimes you just let A be 0. Does that make sense? So if you want it centered at 0, then put in A as 0. But this allows you to put it anywhere. So that's why this chapter is called Taylor series. And that's why I wrote Taylor series at the start, because Taylor is just a more general way to do a problem like this. So let's retry E. Let's try to match E to the X, but at X equals 1 this time. Centered, your book will say centered at 1. Again, I think centered is the wrong way to say that. It's more like a match. Match. Let's match E to the X at X equals 1. Okay, well, let's see what happens this time. Well, all of our derivatives, the derivative of E to the X is still E to the X, but notice, I'll just write a few of these down. So but at X equals 1, the slopes are actually not 1, they're E. Does that make sense? All of our slopes this time are E. Well, that's why our last one didn't work, because we had slopes of 1. That's a totally different slope over there. We have slopes of E at this point. We have a different slope. Oh, okay. So that means our polynomial model for E to the X, same exact equation, but just in a different location, would be f, the original function. We're thinking of, our original function, f of x equals E to the X. So we're evaluating that at A, our A value, our A is equal to 1. So that's E. So our first term is E, and that will slide it up. I can't remember who said that, but you were saying, yeah, it kind of looks the same, but we got to slide it up now. Well, notice instead of being 1, like the previous one, now it's E. Well, see, that's going to move it up because E is 2.718. It's going to move a little bit higher. And then plus f prime of A, which is also E, divided by 1. So it's still 1. And then this is x minus A. Well, our A value is 1. And so every one of these is going to be E, but now it's E over 2 factorial. X minus 1, and then E, I got to add all the exponents. So we have x minus 1 to the 0 power here, but since that's 1 anyway, I just didn't write it down. So then we have to the first power to the second power. This is E over 3 factorial, which is 6, and now our x minus 1 is to the third power, and so on and so forth. So now that'll be, if we go back to Desmos, that will look like E to the X as well, except for it'll be closer to 1 now. It'll match up at 1, not at 0. And so do you see what changed? It wasn't, I did replace x minus 1, but notice the key change here besides that is the fact that, these used to be 1s. Well, now they're all E's. And so I got to change all of those and then it'll match. So they have a different slope. That's the issue. It's totally different slope over there. Well, let's go take a look. So maybe I don't want to get rid of this one, so I'm going to just copy it. I'll name it something else. I'll turn that off because maybe I want to turn it back on. So we're saying, okay, yeah, this is all good, except for these slopes were not ones, they're all E's. Aha, yeah, look at that. I'm gonna graph the point. 1E, just so that we can see it. So see how it's a good match now. But now it's centered at 1. That's kind of cool. So armed with this, does it make sense you could use that as an estimate now for, say, e to the 1.1? If you wanted to know what's the answer to e to the 1.1, you could plug 1.1 into that expression and it would pop out a pretty decent estimate for what your calculator would give you. Again, I don't see that as super valuable because we have an exponent button. But that's what a Taylor series is actually doing. Now we can kind of match any place we want to match. Now, we don't really care if there's a ... on the end of this, right? Because if it goes forever, then it's going to be an exact match everywhere. So we don't care where it's centered. But realistically, what this is for, why people, if you will, invented this, was because it allows you to make estimates for things that are kind of weird, kind of complicated. So you just kind of figure out how many terms you want to have. So I have a P3 polynomial here. I have a third degree polynomial that's a match for this. And then, hey, look, I only have to do multiplication and addition and I guess a little bit of subtraction here, and I can actually get an answer to some complicated expression. And I don't need infinitely many terms. So I can stop at just 4 terms and 4 terms, but a cubed polynomial. Notice and pay attention to that assignment. I can't remember if that's tricky, but if they say, you know, write a 4-term polynomial, notice this is 4 terms. Now it's cubed, it's a cubic equation. So if they say degree 4, then that mine answer doesn't work because it's degree 3. But if they said 4 terms, then, oh, I got 4 terms. There's 4 plus signs. 3 plus signs makes 4 terms. And you might remember sine the other day actually alternated, like it had like an x and then an x cubed and an x to the 5th, like a whole bunch of terms were missing. So let's try that. Let's try cosine now. And again, we'll notice some terms are missing with that. So the larger magic here, the thing you don't want to miss is, wow, you mean you can actually replace every function we've ever learned with just polynomials now, which again are renamed as power series. The answer is, yeah, that's exactly right. So you do this with cosine. And just so that we get a little bit of practice with this, I'll leave that in the screen so that you can see the Taylor series expansion up there. Let's try this for f of x equals the cosine of x. And we'll say centered at, let's see, is 2 a good idea? No, 2 is not a good idea because the cosine of 2 is not a nice number. So we need to pick something that's nice, like pi over 2, like sine and cosine like pi over 2, right? So let's center it at pi over 2. So I want to give you a head start. Remember, you need f of x, you got that. You need the derivative, the second derivative, the third derivative. Let's take it all the way out to the 5th. So let's make a degree 5 polynomial for this. Actually, let's make it 6. Let's make a degree 6 polynomial for this. Just gonna give you a second to get a head start and then catch up to you. I'm gonna start catching up to you. So let's see.
Is this gonna be weird? Because we're gonna have holes in terms.
Yeah, that's right. There's gonna be some issues here. So think about pi over 2. Pi over 2 is 90 degrees, and 90 degrees is at the point 0, 1. And since the x coordinate is the cosine, and the y coordinate, as you remember, is sine. Anytime we have a cosine, there's not going to be a term. So the cosine of pi over 2 is 0. The sine of pi over 2 is 1. So you're exactly right. So let's see, what do we got? So if f of x is cosine of x, then f of pi over 2 is actually 0, cosine of pi over 2. So, oh, that's not good. And then f prime of x, we say the derivative of cosine is negative sine of x. And so f prime of pi over 2, since the sine of pi over 2 is 1 and there's a negative in front of it, then we have negative 1. So these are our coefficients, remember. And then the derivative of the derivative of sine is cosine, and the negative comes along for the ride. So the second derivative of pi over 2 is actually back to 0 again. So there's a term that's entirely missing. Third derivative of cosine is negative sine. The negative and the negative cancel out. So now we have the sine of x. And the third derivative then evaluated at pi over 2 is actually 1. And so notice we're getting zeros every other answer. So the fourth derivative, the derivative of sine is cosine. Notice we just got back to the start again. And the fourth derivative then evaluated at pi over 2 is actually 0. So there's no term there. I got 2 more to do. So then there's this fifth derivative. Derivative of cosine is negative sine. We already know this. This is the same as I think I'll go ahead and write it out. Like we're back to here, right? So we know that we kind of, there's a pattern now. I wouldn't have to write any more of this. It's just going to repeat the same 4 pattern. But I will, since we're just kind of learning this. Derivative of sine of pi over 2 is 1, but then there's a negative in front of it. So there's my next coefficient. And then the 6th, which is not, I guess, not worth really writing out, just because the derivative of sine is cosine, and we saw that sine always, or cosine always produced nothing. So the 6th derivative of pi over 2 is actually 0. And so, okay, we're tired, right? We got a good model for this. We got a model for cosine at pi over 2, and now we got all these coefficients. And so now we're ready to write out the Taylor polynomial for this. It's kind of hard to see this all at once. I guess you can just remember those. Let's see, it started at 0. So again, I want to write everything out. So I'm going to say polynomial this time. I'm going to say P6, because this is the way I said it kind of in your assignment, is like the 6th degree polynomial. This is the way I say it on tests where your book says it. Doesn't matter. It's just a function. I mean, call it f of x. It's the same thing. It's the same as cosine. But I'm saying, hey, I'm going to quit at 6 because I'm tired. So it's the same every time. What do? We start out and we say, let's see, I'm going to run out of room. So I'm going to make this small. P6. So I say, okay, what do? I take the, let's see, the slope. Okay, I got all the slopes. I got the first one was it 0 or 1? 0. I got 0 over 0 factorial times x to the 0. What's wrong with what I just wrote?
Forgot the minus pi on 2.
Yeah. It's minus whatever your a value is. But notice everything there goes to 0 thanks to the 0, like 0 factorial is 1 and x minus pi over 2 to the 0 is 1. But unfortunately, the 0 at the top actually makes that term nothing. Then my next derivative was -1, was it not? -1 over the top of, why is something wrong here? Something feels wrong. -1 over the top of 1 factorial, and now we're x minus pi over 2 to the first power. And then the next term was 0, so I'm going to leave it off this time. And then the term after that was 1. So that 0 is going to make this next term disappear. Maybe I should write it. Plus 0 over 2 factorial times x minus pi over 2 squared. And this went to +1. The cubed derivative was +1. So 1 over 3 factorial x minus pi over 3 cubed. And it's coming around a room there. Plus 0 over 4 factorial times x minus pi over 2 to the 4th. So that term's going to go away. And then our fifth one was -1. So -1 over 5 factorial x minus pi over 2 to the 5th. And finally our 6th, but 6th is going to be 0. So it added nothing to this. All wasted time writing it down. So really then, if we were to clean up that mess a little bit, just to see what we actually have without the 0 terms in it, don't I have minus, so I'm looking at this term here. Don't I have minus x minus pi over 2 to the first power? And I'm looking at this term, 3 factorial is 6. So I have plus 1 over 6 x minus pi over 2 cubed. And then I'm looking at this term, minus 1 over 5 factorial, which is 120 x minus pi over 2 to the 5th power. And so notice I'm not saying dot, 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 because I didn't say, that's not what f of x is equal to. I said 6. I want a 6th-degree polynomial. Well, there isn't 6 of them. There's 3 terms. Notice they alternate. That's kind of cool. Alternating series. So the question is, does this actually match what cosine looks like at pi over 2? That's what we want to see now. So let's go over to, so any comments on that? Is there any mistakes we made? Do you feel good about that?
It looks good, yeah. That's what I got.
Okay, that makes me happy. So let's go back to Desmos, just slow down, give you time to soak on this a little bit.
So Doug, on the test, if you wanted a 6th-degree polynomial, we would have to go essentially to 12 on this problem, right?
Well, not degree, term. If I said
Yeah, accounting for the
polynomial.
zeros.
Yeah, and I would not, on a test, I would not say find a 6th-degree polynomial for this if there wasn't a 6. I would have made a key and went, oh, that was dumb. There is no 6th one. I always said make it 5. So in this problem, I would have said make a 5th-degree polynomial. Good question. So we have the cosine of x, which we know looks like that. Let's see, should I save these? Maybe that'll save me some trouble. Let's graph the point that this is supposed to match at, which is f of pi over 2, right? So if I graph the point pi divided by 2 for x, and then I graph f of pi divided by 2, isn't that the point we're saying it's supposed to match? It's supposed to look like that. It's supposed to match right here. So let's begin building this thing. I think I'm just going to get rid of that, start over. So I don't know what to call it. I'll call it g of x this time. So we're saying it equals negative x minus pi divided by 2. And that's raised to no power at all. So notice it's working. It is unacceptable for that to be the same color. Notice so far so good. Now again, what is that? That's the best match for cosine you can get if you limit yourself to a line. Why is it a line? Well, isn't that x to the first power? And it's been slid right pi over 2 and it's been flipped upside down. And so notice it's working. It actually matches that the best you could possibly do with a line. Now we say, well, let's add a parabola. Well, remember the parabola was gone, like the parabola didn't help. That's kind of what's happening. Our next term for this was actually a cubed. And so we said, if you add 1/6 and then multiplied by this, copy, paste, except raised to the 3rd power, yeah, that is cool. So effectively adding a cube term made it stay with this a hair longer. By the way, while I'm thinking about it, I'm going to quickly go. I'll forget to say this if I don't say it now. In your most of the times the videos that I stuck in here are, just individual. You probably never watch these unless you have trouble. Don't you find yourself only watching the videos that are inside the assignment? Like it's specific, but here in 11.3, notice there's actually 11 videos here that I threw in that are kind of teaching videos, if you will. The videos you probably watch are the ones that are paired with the assignment, but these 3 right here, 3 blue, 1 brown explanation of the Taylor series formula, and then Khan Academy has a part 1 and part 2 that kind of explain what I'm showing you right now. I'd highly recommend you watch those. Just because they kind of take a little bit more of a theoretical approach, but we're watching it happen here. Do you see how this green curve is growing to match the red curve closer and closer and closer the more terms I add? This is really cool. This time I'm actually going to keep that one and then add 1 more term to it so that we can watch the old one improve. Let's see, except for it wasn't 1/6, it was 1/20 because it was 5 factorial. And then it was a minus sign because it alternated, and then it was not raised to the 3rd power. it was raised to the 5th power. So look how much longer the blue curve stays in contact. We've seen this before, right? It's staying in contact longer than the green curve did. And so, does it make sense, if you will, you're an ancient person and you'd like to know what the cosine of 3 is? So here's the payoff. Let's do it. So let's just get rid of that. You would like, now let's pick something better. You'd like to know what the cosine of 2 is. Now, do you understand that if you don't have a sort of a modern calculator with a cosine button in it, you're not getting the answer to the cosine of 2. So we can down here say, you know, what's the cosine of 2? And, you know, it tells us negative 0.416. But up here, we can say, here's my estimate for G of 2. Notice how darn good that is. And again, what math are you doing to get, we're cheating because we live in the modern age, but what math is an ancient person doing to get negative 0.416? Well, notice how it's accurate out to the tenths, hundreds, thousands, 10,000. It's out to the accurate to the 100,000th place. It's only off by 1/1,000,000th, and we only have 3 terms. That's amazing. But what did the ancient person have to do to get that answer? They had to multiply, divide, add, and subtract. Does that make sense? They didn't have to. I mean, that's really cool. So in a sense, that was the impetus behind the invention of this idea. Do you see the pattern to this? Like, could you add the next terms here yourself? What would the next term for this be?
Be a plus.
Be a plus, because it's alternating.
What's 7 factorial?
Nice job. We don't even have to figure that out. Just type 7 factorial. So you're noticing it went 3 factorial and then 5 factorial and then 7 factorial. Your Desmos, and let's see, not your graphing calculator, but Desmos actually knows that in this context, that means factorial. So I don't even have to figure out what it is. And then it's x minus 2 raised to the 7th power. Even better. And so this is what we saw happening with sine the other day too. If I just keep adding terms to this, if I grab this plus sign right here and change that to a 9 and change this to a 9.
Remember, you can actually type in the summation symbol.
Yeah. And isn't the summation symbol even better? Now let's play with that for just a little bit, because that's a little more challenging. Summation symbol. Let's see, what would that be? I'll call it Taylor series of x equals, let's try that one more time. Remember we were going out the door with this because we ran out of time last time, but we saw that it was very hard to write the summation for this. Let's see if we can survive it today. So we're going from 0 to infinity every single time, except for, let's see, I have 9 up there right now, right? I went out to the 9th term, n is 9. That's what I got shown right there. Again, notice that's only 1, 2, 3, 4, 5 terms. It's 5 terms, but it's a 9th degree polynomial. So let's see, what was our pattern for this? Well, we need an alternating. The easiest way to get alternating is just to say minus 1 raised to the n. Now, is that going to work, or does it have to be n or n plus 1? Is it going to work? If I put n as 0 in, does it work? If I put n as 1 in, does it work?
It works, I think.
Notice.
Because if you put n to the, wait, but if you put n to the 3 and it doesn't work.
Yeah, good job. In other words, it seemed like it worked because this is our n is 1 term. And if you put n is 1 into this, you get a negative, and we're supposed to get a negative. But then Eve astutely noticed, hey, wait a second, when we put 3 in, negative 1 to the 3rd is also negative, and this isn't negative. So we saw last time that was a little more complicated in that, since it was going up by 1, we actually had to double it. And
Didn't you have to divide by 2n plus 1 as well? I feel like we did
yeah,
that.
like it got complicated. Remember that? And so let's just play around with this for a little bit. So that was like our we know it has to be 2n, or then, and maybe even like 2n plus 1. Does that work? Oops, that's not the right location for plus 1. I think we decided last time I had to put it in parentheses to get it to stay up there. Like, does that work? So let's see if I put 0 in. If I put 0 in, that'd be -1 to the 1. If I put 1 in, that'd be cubed, -1 cubed, that'd be -1. If I put 3 in, notice that's 6, that's 7, -1, it's still producing negative numbers every time. Maybe that doesn't need to be there. So if I put 1 in, 2 to the 1 is 2, -1 squared is positive, so that's not right. That doesn't produce the,
I think maybe if we just have n plus 1, and then we just, instead of looking at the first term as each term as being the one with the like the third power, whatever, like the third term being the third power, we just look at them as alternating. So the first term would be first power, but the second term would be to the third power.
yeah, the problem is though, is this is our n. In other words, this is n cubed, this is n to the 5th, this is n to the 7th. Like that's where these terms are coming from. So we literally have to, when we put 7 in, we need a positive number for this. Well, that works because 2 squared, or 2 times 7 is 14, and -1 to an even power is positive. But does it work with this one, 5? No, because 5 times 2 is 10, and -1 to the 10 is also a positive number. So that doesn't give us the right sign there.
Yeah, all those zeros in there are important.
Yeah, the zeros are important. So we can't, over here, we can't say, skip one, like go 1, 3, 5, 7. We have to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the zeros will cancel themselves out on their own. Do you see how hard this is? Let's see.
Does n minus 1 work?
Yeah, maybe it's -1. Does that work? So if I put in 3, notice you get an odd number every time when you do that.
I feel like it has to do with the other stuff in our equation. It's based on that. So like we have to, maybe if we use the 2n plus 1 in our
Well, does it have to be 2n?
equation.
Or maybe it doesn't have to be 2n. Well, let's leave that for a second. We're suffering. So notice we got lucky on top and that it was 1 and 1 and 1 every single time. So I can at least say times 1 divided by n factorial. Is that true? Except for on the top was a derivative, right? So the derivative is actually what produced the plus and the minus sign, right?
This is gonna sound really weird, but can you put on the top d dx times cosine of x and that, but say d dx to the nth power? So it's like 1 and then it's -1 and then it's, does that make sense? I don't know if that works.
In our case, we get kind of lucky that all of our derivatives are just ones. Does that make sense? Because if it wasn't for that, we'd have to do exactly what Eve just said, which is the top of this is not, in a sense, in the real world is f prime of pi over 2 and f double prime of pi over 2 and so forth. And so, yeah, I mean, it's like there's some way to write that down. Well, in our case, we know they're 1 every time. And so we kind of get lucky. We just have to get the sign right. Does that make sense? So we actually don't have to go to that trouble. And then isn't it always x minus, keep hitting the wrong thing, x minus pi divided by 2 Raised to the, is it just raised to the nth power?
Maybe raise that to the 2n plus 1.
So let's just stare at this part. Is this working over here? Let's just stare at this, just that. Is that working? If I stick in n is 0. Maybe that's a +1. So if I stick in n is 0, then this is x minus pi over 2 to the first power. Hey, that's that term right there. Except we got to somehow get a minus sign out in front of it. And then if I stick in n as 1, that becomes 2 times 1 plus 1, that's third. This is working. Do you agree with that? Like this is producing, if I start at 0, do you agree that this is producing these terms? And then if I move to n is 2, that becomes 2 times 2 plus 1, that's to the 5th power. That's working. Do you agree with that? Whew, we got something to work. But is this working? Like this term right here came from when n is 2. N is 2. Well, this is saying that'd be 2 factorial. So we want those to match. So don't we want this to also be here?
And then the alternator could just be to the nth power.
You think?
Actually, it looks like the alternator is working.
Well, notice this should be an exact match. If we get this to
Oh,
work,
wait, never mind. It's not working.
those two graphs will be identical because notice this is out to the 9th. Wait a second. In this language, that's actually 0, 1, 2, 3, 4. This is actually only 4 terms. Like if we went to 4, this would actually be an exact match. So it isn't, it should be right on top of each other. So you think it's just n. We're getting close.
Oh, wow. That's like the exact opposite.
So we decided it wasn't +1, right? -1, right? Actually, I'm a little surprised. Most of the time, I'm just acting like I don't understand, but actually this place, I'm actually a little stuck. Seems like that would make it alternate. Maybe it's n+1. Yeah, I think that's what it is. There we go. Oops. It's in the parentheses. I think it's n+1. We're getting darn close now. Let me turn this one off for a second. See how that is modeling it? That's working now. So when this was just an n, the only reason it didn't work is the first term. And by the way, this term right here is the n equals 0 term. Well, when I put n here, -1 to the 0 is 1. Like that actually gave a positive answer. So by adding 1 to it, that actually fixed that.
Oh,
But if we go from 0 to 4, do you agree that's actually 5 terms? 0, 1, 2, 3, 4. 0 to 4 is 5 terms. That's the problem. How many do I have up here? 1, 2, 3, 4, 5. No, it's the same. They should be the same. They're not. But I actually think it's just 1 too many terms. If I take this to, I think 3, is that going to be exactly the same? Huh, that's weird. This is so close, but
On the blue g of x graph, is it supposed to be -1/9 factorial?
yes, a stupid mistake. Notice the plus, minus, plus, minus, plus is supposed to be a minus. That's the reason they didn't match. Our graph was correct. They were the same. We finally sort of got it down here, if you will. There we go. Good save. Not sure how long I would have stared at that. How come we didn't notice that? Like, what? You mean you got the entire sign wrong? Why didn't we notice that? Like, why isn't the graph just terrible because of that? Well, isn't that term really tiny? That's why. It's a tiny number. So whether you add or subtract it didn't make a huge difference. It made a difference, but not a huge difference.
It off down the line.
So yeah, down the line, it would have started causing problems. And so I think we finally got it right. But do you see the value of writing the kind of the sigma notation and how kind of challenging that is? That's not going to be a big part of this section. But of course, now that we got that figured out, in a sense, what we've done here is, do you agree that all we have to do is write infinity here, and then we can actually say t of x and f of x are equal? Up here, we can never get there because it's always kind of like, I quit, I'm tired, I can't go far enough. But down here now, of course, I can say I would like to have, remember 0 to 4 is 5 terms. So again, we're getting dangerous here. But if I throw 12 in there, notice it starts to grow and grow and grow. And this is looking just like it. Let's go out to 30 terms. We saw that it suffered vastly the other day trying to handle that. Look how long it's taking. But it's like, man, that's amazing. Notice it actually doesn't make any difference what you have it centered at, because it's matching the graph perfectly everywhere now, right? So if I replace this 30 with infinity, then I can actually say this is equal to the cosine of x. And again, as I said the other day, this is why you have a calculator that knows the answer to things like this. Unbelievable. So there is a power representation for everything. Super cool. Now, again, that was a very different equation because we centered it at x over, or at pi over 2. If we had centered it at 0, we would have got kind of a slightly different answer. And actually, let's see, I think I want to show that to you right now. So there is a note sheet you're going to have for the next test, and it looks like this. Common power series expansions. This is something you'd see in your textbook someplace, I'm sure. I just made this myself. But first of all, you know, on the test, like, I don't want you to memorize Taylor series, and I'd like you to, you know, stare at it, like have it in front of you just so you don't make a dumb mistake. But you should see that's what we've been doing. And again, notice that's a Taylor series because it's centered at A. It's not, it's centered anywhere. A can be 0, Maclaurin series. Notice how dumb it looks when you have 4 derivatives. Like, it just doesn't look right. Like, there's just too many of those things. But that's the pattern. And so here's what we discovered. Here's what we discovered Thursday last week. What's the expansion for sine? Sine of x expanded to x minus x cubed over 3. Notice that just says x. It doesn't say x minus a. So this is actually a Maclaurin series because that's x minus 0, right? And then we just did sine, but again, that doesn't look the same as what we just did because we had x minus pi over 2. And this is actually a Maclaurin series centered at 0. So what I don't think I will take the time to do is to let's go find cosine except centered at 0. If we did, we would get that series right there. But what I'd like you to notice here really quick is take the derivative of the sine expansion up there. Remember, there was a time back in Calc 1 when we said, what's the derivative of sine? And we realized, wow, that's a weird equation. How are we going to find the slope of a sine wave? And I fairly quickly told you in my class that the derivative of sine was cosine. And I actually hinted at this. I think I actually showed you this series. You just didn't understand where it came from at the time, at least in my class. But notice if you take the derivative, I think I can write on this since it is now over here. Notice the derivative of x is indeed 1. The derivative of x cubed, the 3 comes down front, and then this 3 cancels with this with 3. Remember, 3 factorial is 3 times 2 times 1. So that leaves 2 factorial behind. And so this derivative of this statement turns into this statement. Same thing happens again, x to the 5th. The 5 comes down front. 5 factorial would be 5 times 4 factorial. So the 5s cancel and you end up with x to the 4th over 4 factorial, which is exactly what's sitting down here. And so sure enough, the derivative of sine is actually cosine. The derivative of e to the x was e to the x. Derivative of sine is cosine. We won't do this, but the derivative of cosine is supposedly negative sine, right? So try that out. You actually get sine, except for all the signs are wrong. Oh, well, if I just made it negative, that would fix all the signs. Notice this note sheet actually gives you kind of some, well, the expansions for all of this. Like, look what happened for E. We just wrote this a second ago, but I didn't bother to write out the expansion for it. Notice every term was just x squared over 2 factorial, x cubed over 3 factorial. So it's pretty easy to write the statement. Oh, it's just x to whatever term I'm on divided by that term factorial. And so notice the summation for it is really simple to write down. We didn't suffer as much because it didn't skip any terms, right? The terms weren't getting skipped. And so that wasn't terrible. And notice this one actually lines up for x's infinity. There is no radius of convergence. Those are equal. You don't have to stay inside a certain range. And the same we just saw was true for sine and cosine. Didn't that just match it forever? Like it matched it forever. So there's no limitation. Stick in anything you want. Notice you're seeing some of the ugly that we saw a second ago. Notice both sine and cosine have that alternation. And so there's the alternation. And then the 2k plus 1 is what caused it to skip a term, right? It went x to the 1st and then x to the 3rd and x to the 5th. That's what caused it to skip a term. And the same thing happens down here because this is x to the 0 and x to the 2 and x to the 4. So those 2k's and 2k's plus 1s cause it to skip terms, if you will, so that every other term is missing. And then notice there's no 1 there because, well, one's just 1. Like if there's nothing there, then it's 1. So it's always 1 over, so if you will, the 1 is missing. It's like 1 divided by that number factorial. Again, that made it go 3 factorial and 5 factorial and then 7 factorial. So it's like, well, why write a 1 up there since you don't need to? So these are listed in your book as common power series expansions. And so, one of my goals for you here is actually that you be able to make these for yourself. That's what's kind of fun. Again, I'm a little less concerned about kind of this part of it. And as you notice, every one of these is just x, not x minus a. So everything you're looking at here, I should have wrote this in the note, but I'd say these are actually Maclaurin series, every one of them. So the one we just did doesn't quite look like this cosine because we had x minus pi over 2. Then that pi over 2 also kind of screwed up the way some of the numbers looked, right? Well, let's see. Let's just do something weird now. And this is the part where I don't like what the book does, because Let's just try something weird. Like, let's try to find the expansion for this expression. Natural log of x squared plus 1 and centered at x equals 1. And I'll do this kind of with you rather than giving you a little bit of time, only because I'm a little concerned about running out of time. And well, I will give you 1 second to think about that, because I'm just going to copy down my expansion earlier for the Taylor series. Duplicate. So there it is. And so we need the first, second, and the third derivatives. And so notice we have f of x, and now we can find f of 1. And notice you need to make these up to come out nice. That's why a minute ago I used pi over 2 and not cosine of 2. Because when you plug the number in, you want it to come out nice. So in this case, I picked something that came out nice. I chose 1. So if I'd have chose x equals 4, that would not have been nice, because we'd be taking the natural log of 16 and we got a really weird number. So I picked 1 to make our life nice. Natural log of 1 squared. Natural log of 1 turns out to be 0. Oh, that's nice. And so f of 1 is actually just 1, thanks to that plus 1. And by the way, that's why I threw that 1 in there, so that it wouldn't be 0. I didn't want any zeros. I don't like it when terms are missing. It just makes it look weird. So there's our first term. Well, then what's the derivative? So now we got to start taking derivatives. This is not a terrible derivative to take. What's the derivative of natural log of junk?
1 over the junk.
1 over the junk. What does chain rule say? We're not done.
You gotta multiply it by the junk,
By not the junk, but what?
derivative of the junk.
Derivative of the junk. So derivative of 2x. And so it's actually 2x over x squared, or just 2 over x. And so if I plug 1 in, f prime of 1, that's 2 over 1, I get 2. So these are fun coefficients, if you will. Nice. Isn't that nice? It came out nice. I spent some time to try to come up with something that came out nice. So notice the natural log just went away. So now we're on to the second derivative of x. Well, you got to think of 2 over x as 2 times x to the negative 1 power. So now it's just power rule. Negative 1 comes down front, multiplies by the 2 to make it negative, and then you subtract 1 from the exponent. So there's that derivative. And in order to plug 1 in, I would rather see it written like this. Oh, yeah, okay, if I put 1 in now, f double prime of 1, that's negative 2 over 1 squared, that's just negative 2. So what would the third derivative be? Well, this negative 2 gets multiplied by that negative 2, and so it becomes positive 4. And then you just lose 1 off the exponent, take 1 away. And so again, to plug 1 in, I'd rather see that as 4 over x cubed. Oh, 4 over 1 cubed. See how nice 1 was as a choice to center this at? No, it's just 4. So notice I'm getting kind of different and fun coefficients. Matter of fact, so fun, I don't want to wait yet. I'm having a great time here. So then the derivative of this, negative 3 would get multiplied by 4. That would become negative 12. That'd be x to the negative 4th. In other words, negative 12 over x to the 4th. So f, the 4th derivative, evaluated at 1, would actually be negative 12. Notice it's actually starting to alternate. Isn't that cool? Can you see it's going to alternate from now on? Oddly, it didn't alternate at the start. It went 1 to 2, but then it went negative 2, positive 4, negative 12. It's going to continue to alternate now. Can you see why that's going to happen? That's kind of interesting. Because in the next term that I am also inclined to write out for some dumb reason, I'm going to take negative 4 times negative 12, and it's going to be back to a positive again. And so I evaluate that as 48 over x to the fifth, which just means the fifth derivative evaluated at 1 is just 48. So notice the numbers are starting to get big, but they're going to alternate plus minus plus minus. That's interesting. So I got everything I need now. I've got all of these terms. That's kind of the key here. I've got all of the hard part. Would you agree that's the hard part right there? Everything else is just x minus 1 squared, x minus 1 cubed, x minus 1 to the fourth, and then it's 1 factorial and 2 factorial and 3 factorial. So like I did all the work. The only thing that's hard is what I just did. So I think I have a model. This time maybe I'm just going to write it as f of x. I don't need to make up a new name for it. I'm just going to say, okay, f of x was equal to the natural log of x squared plus 1. Well, it also turns out f of x is equal to this. It's equal to 1 over 0 factorial times x minus 1 to the 0 plus a 2 over 1 factorial times x minus 1 to the 1. And then we get a minus sign for the first time, but notice the number didn't change. Minus 2 over 2 factorial times x minus 1 squared. So now there's a parabola. And then it turns into a plus 4 over 3 factorial times x minus 1 to the third. And then a minus 12 over 4 factorial times x minus 1 to the fourth. And then plus 48 over 5 factorial times x minus 1 to the fifth. And then I'm tired. Hey, look, I found 6 terms for a 5th degree polynomial for this. And now if I clean this up just so it looks beautiful, what does this whole first term become here? Notice you gotta
0.
stare carefully because it looks like it should be 0, but it's not. Notice that.
Darn.
X minus 1 to the 0, anything to the 0 is 1. And then 0 factorial is even 1. So you actually have 1 over 1 times 1. So that actually doesn't go away like you might have thought. And then the next term is 2 over 1 factorial. That's just 2. And x minus 1 to the first, you might as well write it like that. And then it's minus 2 over 2. So that's actually minus 1. And then 4 over 3 factorial is 4 over 6 or 2 over 3. And 4 factorial is 24. So 12 over 24 is actually just minus a half. And then 48 over, I'm going to cheat on my calculator for this, 48 over 120. If I type 48, this is a good way to cheat, 48 over 120, and then you say convert that to a fraction, it'll give you the reduced answer. That's only 2/5. That's kind of sweet. So plus 2/5 x minus 1 to the fifth. And then I say dot, 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 because I don't know what comes next. Now, would you agree that writing the sigma notation for this would be challenging? And if you did write sigma notation, you would not want to be reducing these fractions like I just did. You would want to do that. And then, you know, look at the weird coefficients we had, because remember, you don't get to write the word derivative in that statement. You got to somehow find the pattern to 1 to 2 to -2 to 4 to -12 to 48. You got to somehow find the pattern in that. It's like, oh, that's really daunting. I don't want to do that. But again, what I want to go do, of course, is go look at this. I mean, we're out of time here, so let's go look at this. Does that really look like this? And of course, this is very exciting because we don't even know what natural log of x squared looks like, right? This is not some common function like cosine of x or e to the x. This is some function that some person made up, that person being me. And I don't remember what this looks like, so I'm very excited too. Let's see. I don't think I'm gonna get rid of sigma because we aren't gonna be capable of writing sigma, right? So our original function is equal to the natural log ln of x raised to the second. Get out of that parenthesis plus 1. And so, oh, that's a cool looking graph. I'm very excited about that. That's kind of fun. You may notice that let's see, natural log of 0. Natural log of 0 is negative infinity. So this is two different graphs. Do you see that? So we're going to end up just looking at the one on the right. Just for the fun of it then, since we said we're centering it at 1, I'm going to actually go in here and I'm going to say I want x to be greater than 0, just so I'm only seeing the right-hand side of the graph. And let's also graph the point we're saying this is going to match at. In other words, it's at the point 1 f of 1, isn't it? So we're saying it's going to match up right there. So let's watch it grow and let's see if we got this right. So we said that first it was, well, 1. It equaled 1. That's the best you can do. If you don't have slope included, at least they match up and they agree that the point 1, 1 is correct. But now let's go add slope. Let's go add the first derivative, which is making the slope match. And we said the slope actually was 2. Type. Yeah, now that you add the slope, it still works at the point 1, 1, but now the slopes match. And so what if we go on and add a parabola? We said that was minus x minus 1 raised to the second. Yeah, it's even better. So we don't need anybody to tell us this is working. I can see that it's working. Again, all you got to do is leave off a sign or something and mess it all up. Let's keep going. Plus 2/3 x minus 1 to the third. Yeah, that's beautiful. It's matching it perfectly. And then it was minus 1/2. Let's add a 4th degree term to it. Bam, go back, get rid of that 2, make it a 4. Yeah, that's even better. Notice, you remember what 4th degree polynomials look like. They have to exit the same way. They either both exit at the bottom or they both exit at the top, whereas cubed or 5th or 7th goes like this, right? So when I add this 5th degree term, 5th and final degree term, plus 2/5, since we decided we were tired. Then being now that it's dominated by a 5th degree polynomial, now it exits the stage one way and the other way instead of both in the same direction. So it's just growing more and more to be like it. Now, why isn't this expansion right here on my little cheat sheet? Well, because nobody cares about this one, right? Like this is random. I just made it up. But the thing that I think is cool about this is I just made up a totally random function, and you can appreciate ancient people could not evaluate this at all. They could not figure out. And of course, now you can see you could probably use this to figure out, well, you know, what happens if you stick in, say, 1.5. Notice this model wouldn't work if you wanted to put 2 in. See how much of a break there is there? I'd need a lot more terms. So we can't stick 2 into this and expect g of x and f of x to match up. But we can stay a little closer to 1 and be okay. And so that's just going to keep getting better and better and better as I go. But the hard part about this one is notice it's very hard to see the pattern. I do see alternation now. I know for sure the next term is minus, and I know the next term is x minus 1 to the 6th, but does it make sense? It's very hard to see a pattern, especially if it's reduced like this. Like I reduced these fractions. If you were looking for a pattern, you're not going to find it when the fractions are reduced like this. But notice it's kind of hard to tell what those constants are doing. Like that's kind of tough. And that's because this is such a weird equation. So sine and cosine and e were really nice equations. So going out the door, I think I'm going to go into my open math, and I'll just so that you have access to it, I will kind of post this, and we're going to spend another part of the day tomorrow kind of looking at some more of this so that you get a little more familiar. But what I'd recommend you to do, like right after you get off this, is go make another one of these. Like go try to make natural log of x plus 1 yourself. Notice that one's really nice. Notice it doesn't say natural log of X. That's weird. Why wouldn't they just make one for natural log of X? Why would they make it +1? That's kind of weird. Maybe you can answer that. I won't answer it right now, but I will tomorrow if you ask me. There's no reason you can't do it for natural log of X, but it causes a problem that you might see. Here's a couple, and notice what's neat about these is they're so nice. Like look at 1/1 minus X, and that's a really weird equation, right? Like how many times do you deal with that? That's really weird. But notice how nice its expansion is. That's it. That's why it's on the list. Oh, that's awesome. So the coefficient's 1 every time. Like I can recognize that pattern. And notice the same thing happens for 1/1 plus X, except for notice it alternates. It goes minus, plus, minus, and they didn't do a very good job of expanding, so you'd see that. This next term right here would actually be minus X cubed. They could have showed you a few more terms so that you'd actually see that pattern. And remember, that's what we started this discussion with is, doesn't this look a lot like A/1 minus R? I mean, that's what we started this with back in 11.1. But the point is now you don't need to memorize that anymore. You just take this little derivative approach and you can take any function you want and rewrite it as a polynomial. That is cool. Huge takeaway. And as I said before, that's why you have a calculator that tells you what the natural log of X is. If it wasn't for these two expansions, you would not have a calculator button for sine, cosine, and tangent. And by the way, where would tangent come from? Well, isn't tangent sine over cosine? You just divide them and then you'd have tangent. And you would not have a natural logarithm button if it wasn't for that expansion right there. There would be no calculator button if it wasn't for that expansion. So this is what, in a sense, made our modern life possible. You've been taking advantage of Calc 3 for many, many classes of math and you just didn't know it. Well, now you know. Kind of cool. So we're just going to play with this a little bit more. I got to shut up. It's 9:29. Stay after if you want. As always, we're going to talk a little bit about air tomorrow and a couple of other small things, play around with a few more series, expanding some other things, and kind of some questions that look a little bit more like what's in your assignment. And, so the only thing you don't know now as far as 11.3's assignment is if they ask something about air, like how much is this off of the final answer? You won't know how to answer that, but we'll talk about that tomorrow.
All right, bye, Doug.
Ciao.
Hey, Doug, did you steal on the MyOpen Math? It says one of the video lessons is from 3 blue, 1 brown. Did you steal my YouTube channel? Didn't
Yeah,
I tell you about that?
yes, you did tell me about that.
That's
Isn't
my
it good?
cheat. You can't go wrong sharing my cheat.
Yeah, that guy's amazing, Eve. You're right.
I know, isn't it crazy?
That
Have
guy's-
you watched anything by Numberphile?
I've heard of that, but not much.
Yeah,
Yeah, I
he
think
does a
about
lot
that
of
too.
really accessible proofs.
Yeah,
Accessible proofs. Does that mean you use the proofs?
Well, like
too mathy.
he did a couple that are like how some infinities are bigger than others, and
Mhm.
they're well explained enough that even though I learned them when I was still learning algebra, I still understand them.
Yeah.
But Doug, so in the past, I was able to open up my Open Math and open up old assignments for practice, and I actually really like doing that before tests just to be able to go over the material.
Yeah.
And now it doesn't let me do that without using
Really?
grade passes. Yeah.
Whoa.
So
Not good.
is there a setting you could flip to change that, or?
I know there is. I'm gonna go find it.
Yeah, that'd be awesome.
That is
I thought my thing was just